Is it working? Okay. So hi, let me just go to the presentation real quick. Really sorry, this is a really bad quality. I was recording another software, but whichever reason, it took forever to download it. So we're not gonna talk about that. So hello everybody, my name is Manny. Today we're gonna talk about finite state machines. And in this presentation, we're gonna be talking about the history of finite automata. We're also gonna be talking about what is finite automata, the basis of finite automata. We're gonna break it down. Once we break it down, we're gonna be talking about DFA, NFAs, Elpson, NFAs, and also meter machines and normal machines. And we're gonna be talking about what it is, along with an example problem and the state in the state diagram as well. It's recording, just double check down. I do not wanna. Okay, so it says recording. There's enough. Okay, we talk about the history. So finite state machines was developed by von Neumann and Morgenstern's automata theory. So von Neumann is this person right here, and then Oscar Morgenstern is the person on the left. However, Warren McCullough and Walter Pitts, who were two neurosciologists, I don't know how you say that. So this is Warren McCullough and this is Walter Pitts. So they were the first to present a description of finite automata in 1943. Their paper entitled A Logical Calculus, Immanent in Nervous Activity made significant contributions to the study of neural network theory, theory of automata, the theory of computation, and cybernetics. Later, two computer scientists, G.H. Miley and E.F. Moore, generalized the theory to much more powerful machines in separate papers published in 1955 to 1956. There are two. Sorry about that. I just want to make sure that my sorry about that. I just okay, it works. Okay. So it says there are two finite state machines called Mealy machine and Moore machine, or named in recognition of their work. It became a branch of computer science. Finite state machines is considered the simplest automata, and Turing machines is considered the most complex. So on to the next slide. We're going to be talking about what is a finite state machine. A finite state machine is a computational model that can be implemented in hardware or software to model and simulate sequential logic. This computing model is based on a hypothetical model with one or more states. Only one single state of this machine may be operational at any given moment. The machine must change its states to execute various operations according to inputs. States and transitions are the most fundamental components of a state machine. The state is a system's condition influenced by past influence and response to future inputs. The first state is assigned as the initial state. This is when the machine's execution begins. The state transition specifies which input causes one state to change to what? Sorry about that. So I think the one that says a machine must change states to execute various operations. States and transitions are the most fundamental components of a state machine. A state is a system's condition influenced by past inputs in response to future inputs. The first state is assigned to as the initial state. This is when the machine's execution begins. A state transition specifies which input causes one state to change to another. States, as well as transitions and outputs, are created following the state machine type. An infinite automata is a simple state machine with two states off and on. And basically, it is represented by a 5-tuple, which is right over here. So Q is the infinite set of states. I, which is this one right here. I know this is I or L. So this symbol right here represents the final set of input symbols. Z represents or is the finite set of output symbols. I think this is delta. I'm not too sure if it's delta. It's the mapping of L times Q into Q called the state transition function. And then it says W, which is this one right here, is the mapping of W of L times Q onto Z called the output function. Then A, which is the set of accept states where F is a subset of Q. And we're going to go over some real-world examples of finite state machines. The first example is going to be coin-separated turnstile. So for this one, the states are going to be locked and unlocked. And the transition for this is going to be pointing a coin in the slot will unlock the turnstile. Pushing the arm of the unlocked turnstile will let the customer pass and lock the turnstile again. Let me just double check my battery. Sorry about that. I'm just double checking now because the computer's right. Reliable. Okay. Second example will have to be traffic light. With the traffic light, the states will be red, yellow, and green. The transitions will be after a given time, red will change to green, green to yellow, and yellow to red. Then the last example is going to be a safe. So safe, the states are going to be multiple lock states in one unlocked state. The transitions are going to be correct combinations move us from initial lock states to lock states closer to the unlock states until we finally get to the unlock state. Incorrect combinations land us back to the initial lock state. And then we go over to the third slide. We're going to be talking about the basics of finite state. So we're going to start over here. So finite state machine is also known as finite automata. It is divided into two broad categories. One of them is finite with output, and the other one is finite without output. So with finite with output, there are two categories, which are Moore machine and Mealy machine. And for finite automata without output, there is deterministic finite automata, non-deterministic finite automata. The last one is Elpson, non-deterministic finite automata. Oh my god, not the battery, bro. It's kind of scary, lucky. Oh, I have to lower down my battery. Just sorry about that. I have to lower down my battery though. Okay. We'll go on to the next slide. So we're talking about finite with output. So finite with output is basically it's similar to the finite automata, except additional capability of producing output. It is also known as the finite state machine or traducer. Finite automata without output is defined by 6 tuples as following. This is the 6 tuples right here. Basically, Q represents the finite non-empty set of states. Sigma represents the finite non-empty set of the input alphabet. And then this one right here, this symbol, represents the state transition functions. And then this symbol, which I think it's delta. I'm not too sure. That represents the output alphabet. And this symbol right here represents the output function. And then QO is the initial state. And basically, we're going to talk about the characteristics of finite automata with output. The first characteristic is that finite automata do not with output. Finite automata with output do not have final stage / states. The second one is that machine generates an output on every input. The value of the output is a function of current state and current input. And then the last one is that finite automata are characterized by two behaviors. Oh my god, this thing's gonna die. The first one is state transition functions, and the second one is output function. Okay. We're gonna go to the next slide. Oh, sorry about that. We're gonna be talking about finite state without output. I think I'm really sorry about that. I'm gonna have to go to the kitchen now. This thing's gonna die. I really hate this computer. Stop that. Como aqui, man? No, la computadora está acá. Yeah, I'm really sorry about that. And my computer's gonna die, and the charger in the kitchen, it charges really slow. Sorry right there, I have to switch spots, make sure this thing does not die. Okay, so we're gonna be talking about finite without output. So finite without output is also known as semi-amortron or transition system. For some weird reason, finite automata without output is not represented by any tuple, but there's 3 categories, which is NFA, DFA, and Elpson. NFA is represented by the 5 tuple, the same 5 tuple set. Also, the user of a finite state acceptor cares only about the final state. If the machine ends in an accepting state after processing a series of inputs, Make sure it's recording. Sorry about that. I'm not accessing the recording. Okay, just make sure it's recording. Okay. If the machine ends in an accepting state, no, if the machine ends in an accepting state after processing a series of outputs, the machine is said to have accepted the input. Otherwise, it is set to reject input. The common application of finite state acceptors is checking a character string for conformance with the regular expression. This state diagram right here is a deterministic finite automatic, which is basically a DFA. Okay, next slide. So basically, milling machine is a finite state machine with outputs. And basically, it is defined by 6 tuple, which is right over here. The Q is a finite set of states. Sigma is a finite set of symbols called the input alphabet. O is a finite set of symbols called the output alphabet. And then this symbol, which I think is delta, not too sure once again, is the input transition function where delta semicolon Q times sigma is going to Q. And X is the output transition function where X semicolon Q times sigma is going to O. And QO is just initial state from where any input is processed. And basically, we're gonna go over a problem. So basically, one problem that I want to go over is basically a problem that says construct a Miley machine that produces one's complement of any binary input string. So basically, we're gonna come up with a binary input string, which is we're gonna start with 10100. Basically, what we have to do now is we have to find the ones complement. Remember, to find the ones complement of this is basically if it's 1, turns to 0, and if it's 0, it turns to 1. Basically, after we find the ones complement of this, it's going to be 0, 1, 0, 11, which is right over here. Basically, now with this, we're gonna go create a meeting machine with this now. So basically, we're gonna start with state A, which is this one right here. Basically, when A receives when A gets 0. Okay, when A gets 0, it's gonna give 0. It's gonna give 1. When A receives 0, it's gonna give the input 1. And when A is getting 1, it's gonna give the output 0. So basically, when you see 0, which is right over here, it's gonna give the output 1. But when you see 1, the output's gonna be 0. This is gonna give you the ones complement of this. And basically, this is how a mealy machine state diagram looks like. So I'm gonna go to the next one, which is more machine. So more machine is another finite machine with output. It is defined by the same 5-set tuple as mealy machine. Since we'll go over an example, which is basically this one or a problem. The problem says construct a more machine that prints A whenever the sequence 0, 1 is encountered in any input binary string. So we're gonna start with sigma equals bracket equals 0, 1. Basically, the output is gonna be A and B though. That has to be our output. It's gonna be A and B. So we're gonna go over the first one. So let's see right now. So this is our sigma or outputs could be 0s and 1s, and our output or delta will be A or B's. We will first assign this into a DFA. We will come okay, so first, in order to make a more machine, we have to make a DFA first. We will first start with A. So we're gonna start with A, which is right over here. We're gonna start A as a starting state. And A will go to the next stage B, which is right over here, when we get input 0, which is right over here. And then B will go to the next stage, which is C, which is getting input 1. And if A gets input 1, it will stay in itself. So be right over here. And if A gets 0, it will go to B. And if B gets input 1, it will go to C. And if it gets 0 right over here, if B gets 0, it's going to stay in itself. So let's say we go to C, right, which is right over here. So if we go to C, let's say we go to C by the sequence 0, 1. So if we get sequence 0, we're going to be in B. If we get sequence 1, we're going to be in C right now. But if we get 0 again, we'll have to wait for another one. And if we were to get another one in C, we'll have to send it to B, which is right over here. And then if we were to go to by C, which is 0, 1, 1, we can only move ahead if we get another 0, 1. And in order to get that, we have to send C to A, and then we'll be able to get the sequence 0, 1. If C were to get input 1, we'll have to send it to state A. And now our DFA is complete as of that. In order to convert this to a Moore machine, we will have to give the output A to C, which is right over here. So whenever the binary string reaches the state C, it knows that it will have the binary string has to be 0, 1, because remember 0, if you get 0, you go to B. If you get 1, you go to C. And then basically it will also print an A. And for the other case, we don't care. So we'll print B in state A and B. It will print B in state A and B. Okay. If we get input 0 in state A, which is over here, we will go to B. And B prints B. For the input 0, 1, 0, which is right over here, we are getting BAB, which is right over here. This is gonna be your output right here. So basically we encountered in this problem, we encountered the sequence 0, 1, and A was printed. So we'll go to the next one, which is Milli machine versus Moore machine. We're gonna be talking about the differences between both of them. So one difference between both of them is that the output for Milli machine depends on the present state and present input. And for Moore machine, it depends only upon present state. Another difference is that Moore machine has more states. Another difference is that between both is that for Milli machine, the value of the output is a function of the transitions and the changes. When the input logic on the present state is done, and for Moore machine, the value of the output function is a function of the current state and changes at the clock edges. Whenever state changes occur, lastly, the last difference is that Milli machines react faster to inputs and generally react in the same clock cycle. We're going to go to the next slide, which is DFA, or deterministic finite automata. So basically, this is a finite state machines that accept or reject strings of characters by paraphrasing them from a sequence that is uniquely determined by each string. The reason it's called deterministic is that it can fulfill two conditions, and it is also represented by a 5 tuple set. So basically, Q is a finite set of states. Sigma is a finite set of symbols called the alphabet. I think this delta, once again, I'm not entirely sure it's delta symbol, is the transition function where delta semicolon Q times E or times sigma is going to Q. And once again, Q always initial state, and F is a set of finite state / states of Q. So basically, we will go over an example problem. So first problem is going to be L1 equals set all strings that start with 0. And basically what we're going to do is we're going to come up with all of the things called binary string. I'm not sure that's the correct terminology for this. We're going to do 0, 0, 1. We're going to come up with just a couple of them. And we're going to put 0, 0 because the list is going to keep on over and over again. So basically, oh my lord, I'm really sorry about that. So basically, to do this problem, we will start with state A, which is the initial state. If we get input 0 in this state A, we will send it to the next state, which is B. And we'll make the state double. We'll make the state double. And once it's double, that means this is the final state. Whenever a string reaches the final state, that means that the string is accepted. And if it doesn't, that means the string is rejected. After reaching the final state B, which is right over here, after that, whether it's 0 and 1, it will stay in the final state itself. So you have 0 and then 1 over here. In order to make this DFA complete, we have to mention that we have to say what will happen if input A gets input 1. So basically, if it does get input 1, we will make another state, which is state C though. And whichever input we get in state C though, it's just gonna stay in itself though. And the thing is that state C is a dead state though, and basically, once we reach the state C though, we're just trapped in there, and it cannot reach the final state anymore, and the string will be rejected as a result of that. And as a result of this, the DFA is complete. In order to make sure that this DFA is correct, though, we will test it out with the string. So we're gonna test out string 001. We're gonna start over here though. Basically, we're gonna start with 0. So if A gets 0, it's gonna go to B. Since we got 0 again as our second string, it's gonna stay in itself. Since we have 1 again, it's gonna stay in itself in B though. And since B is a final state, that means this is correct, and also the string is accepted as a result of that. We're gonna go to the next one. We're gonna be talking about NFA or non-deterministic finite automata. So basically, it is another finite state automata without output, and it is represented by the same 5 tuple set as deterministic finite automata. And basically, we're gonna go over an example problem for this one. So basically, a question could be construct an NFA that starts AB where sigma equals equals A and B. So we're gonna say we're gonna come up with all the string of A, B, A, B. Remember, first it has to start with A, B though. And after that it could be any letter. So this is the minimum length has to be 3 states though in total. So the initial, the middle one, we have the final state though. So let's say we have so we have A, and we have A as the first value, it's gonna go to B. And we get B though, it's gonna go to C. And whichever value is A or B or A or B or BA after A, B though, it's gonna stay in state C though, due to it being a final state, and also because there's an arrow right next to it though. And since what matters is that the first two have to be A and B, and after that, the input doesn't really matter. And since C, since it's gonna stay in itself in C, and C is a final state, that means the string is now accepted as a result of that. So we're gonna go with Elpson NFA or Elpson non-deterministic finite automata. So Elpson non-determined or NFA or Elpson NFA has null or Elpson transitions from one state to another. It is also called a null NFA or null lambda. A regular expression for a language forms an Elpson NFA. The Elpson NFA can be converted to a simple NFA and then can use the simple NFA to make a deterministic finite automaton or DFA. No closure is required to convert an Elpson NFA to an NFA. It is almost represented by the 5 same tuple set as NFA and DFA, except that the symbol delta, which is this symbol right here. And basically, this means that any state getting any particular input go to any of the Q states or go to no states. And also union Elpson, which is right over here, means that the state on seeing nothing or seeing an empty symbol or could go to one of the states. Every state on Elpson goes to itself. Basically, the only difference between the Elpson NFA and a regular NFA is just basically the Elpson symbol, and also just a change of the Elpson tuple. Just one symbol of the tuple set, and basically that's it though. In this slide, we're going to be talking about the differences between NFA, DFA, and Elpson DFA. So one difference between all three of them is that so for DFA, a single transition for each input symbol, 2 or more transitions for any of sigma and Q for NFA, and for Elpson DFA, 2 or more and Elpson transition for any sigma and Q. All are represented by the 5 same tuple set, except that most of them, I think there's like 2 of them, or all 3 of them. It's either 1 or 2 modifications to a symbol in a tuple set. And also another difference is that NFA can use empty string transitions, but DFA cannot. NFA is easier to construct than a DFA. All DFAs are NFAs, but not all NFAs are DFAs. DFA is understood as one machine, but NFAs can be understood multiple little. Okay, but NFA can be understood multiple little machines computing at the same time. And we're gonna be going over the source real quick. So let's just click this link real quick. Okay. And basically right here, this is all my sources that I use for my presentation. And that is it. Once again, I'm really sorry about this presentation though. I recorded in another screen recorder, but unfortunately, had a lot of issues exporting the file, and also quality was really bad. It was like half an hour the recording, and also the quality was really bad. The watermarker was really big. I heard the exporting was a nightmare. It was gonna take more than an hour, and I think the FPS was only like 15 to 30, which is really low, and the recording was gonna be really laggy, so I had to re-record the whole thing. So once again, might have messed up something or might have gone too fast. So once again, I'm really sorry about that, and thank you for listening to my presentation.